So we are on, okay. So last week we discussed week 1, okay. Now we are going to discuss week 2. So again, this is for automata and formal language theory. So the course learning outcome or objective for this topic is by the end of this module, a student is able to 1. Define automata theory, 2. Define finite automaton, 3. Differentiate DFA and NDFA, 4. Differentiate mealy and more machine. So again, the topics covered are automata, definition of finite automata, alphabet and strings, and language. So what is automata? So again, automata is derived from the Greek word automata, which means self-acting. So an automaton with a finite number of states, okay? So if you are familiar with this one, okay, we have the 5-tuple notation. So this is the 5-tuple notation. So please remember that it should be in order, the 5-tuple. You cannot jumble it up or you cannot mix it up. So when you say Q, this means the states. When you see the sigma symbol, okay, or the summation symbol, it means the alphabet. When you see the symbol, it means the transition function. When you see the symbol Q sub 0, it means the initial state. And when you see the F symbol, it means the final state. So again, the order of the 5-tuple notation are states, input alphabet, transition function, initial state, and the final state. So again, please do remember the order of the 5-tuple notation. So related terminologies. So again, alphabet is any set of symbols wherein you're using the, of course, the summation or the sigma. So next is the string. This is a finite sequence of symbols taken from the alphabet. So when you say length of a string, I think we discussed this last meeting. So this is the number of symbols presented in a string or the number of alphabets. So when you see this symbol, if you remember this one, okay, the alphabet symbol with an asterisk, it means the clean star. Okay, you can call this as clean star. Okay, this is a unary operator on a set of symbols or strings that gives the infinite set of all possible strings. Okay, of all possible lengths over the alphabet. Okay, so set of all possible strings. That is the clean star. So when you say clean closure or plus, by the way, should be, sorry, let me correct this one. Okay, this one should be plus. Okay, this is plus. Just exchange the asterisk to plus. The set of the alphabet or the clean closure plus is the infinite set of all possible lengths. Okay, so the clean star is for the set of all possible strings. The clean closure or plus is the set of all possible lengths. Okay, that's the difference between those two. Then language, this is a subset of the clean star or for some alphabet. Okay, it can be finite or infinite. Okay, so those are the terms that you have to remember when you are studying automata. The alphabet, the string, the length of a string, the clean star, the clean closure, and the language. So now let's try to discuss the deterministic finite automaton or what we call the DFA. Okay, so again, this is called as the DFA because it can determine the state which the machine will move. Okay, so wherein there are finite number of states, okay, so that is called as the DFM or the deterministic finite machine or deterministic finite automaton. So the DFA is also presented by the 5-tuple notation. So again, this is the 5-tuple notation. So the 5-tuple notation is again in order, wherein the order is what? States, alphabet, transition function, initial state and the final state. Okay? So, finite automaton. So, this is an example of the finite automaton. So, each circle represents a state of the automaton. One special state is designated as the start state. The automaton is run on string. Input and answers yes or no. Let's try to discuss this finite automaton. Okay? So, again, this is the starting state. Why? Because as you can see here, there is an incoming arrow that indicates the word start. Okay? And of course, we have the accepting state or the final state, which is indicated by the double circle. Okay? And then next, the Q0, the Q1, the Q3, and the Q2 and the Q3 are the states. So every single represented, every single circle here from Q0 to Q3 are what we call the states. And of course, the 0 and 1s are the inputs. Okay? So that is the finite automaton. So now, let's try to, let me clear my marks. Okay, let's try to create the DFA of this finite automaton. How are you going to create the DFA? Let me use my pen. So to create the 5-tuple notation of this finite automaton, I will write the 5-tuple notation. Okay. So what is the first one, class? What is the first one? What is the first symbol in the 5-tuple notation? That would be what? That would be states. So what are the states? I am going to write all of the states. I have Q0. I have Q1. I have Q2. Please bear with my writing, class. And then I have Q3. Okay, so again, the first, this is parenthesis. I'm sorry about that. This is parenthesis, closing parenthesis. So the states are Q0, Q1, Q2, and Q3. So next, what's the next symbol for the 5-tuple notation? After the states, you have the input alphabet. So what is the content of the input alphabet? I have zeros. I have 1. Okay, so that is the alphabet. What's the next one? The transition function. So I will write the transition function. Next, what is the next symbol for the DFA? Initial state. What is the initial state? The initial state here is Q0. So I will write Q0. Okay? Last one. What is the last symbol? F, which means what? Final state. And what is my final state? My final state is Q2. So now I am going to put Q2. Okay? So this is the 5-tuple notation of this finite automaton. Okay? So remember that, class. So later on, I am going to discuss how to get the transition function. Okay? Let's move to the next slide. So DFA or deterministic finite automaton is represented by diagrams called the state diagram. So by the way, this is a state diagram, this illustration. So the vertices represent the states. So what we call the states are also sometimes vertices. So the arcs are the arrows are labeled with an input alphabet show the transition. The initial state is denoted by an empty single incoming arc, and the final state is indicated by double circles. Okay, so don't forget about that. So sometimes the initial state is called as the starting state. The final state is sometimes called as the ending or the accepting state. It's the same. So next is the non-deterministic finite automaton. So what's the difference between the deterministic finite automaton and versus the non-deterministic finite automaton? Okay? So when you say NDFA, okay, it is for a particular input symbol, the machine can move to any combination of the states in the machine. So in other words, the exact state to which the machine moves cannot be determined. That's why it is called as non-deterministic. Okay? So as you can see here at the bottom, we have the same symbols here for the non-deterministic. The NDFA or the NFA also uses the 5-tuple notation. We have the states, we have the input alphabet, we have the transition function, we have the initial state, and we have the final state. So this is the NFA. So let's try again to compare. Let's try to summarize the DFA versus the NDFA. So DFA, the transition from a state is to single particular next state for each input symbol. So hence, this is called as the deterministic. While the NDFA, the transition from a state can be multiple next states for each input symbol. Hence, it is called as the non-deterministic. The DFA, okay, in the DFA, empty string transitions are not seen in DFA. While in the NDFA, it permits the empty string transitions. In the DFA, backtracking is allowed. In NDFA, backtracking is not allowed or not possible. Okay, so DFA requires more space and DFA requires less space. In DFA, a string is accepted by a DFA if it transits to a final state. In NDFA, a string is accepted by an NDFA if at least one of all possible transitions ends in a final state. So this is the summary of the comparison of the DFA versus NDFA. So next is acceptors, classifiers, and transducers. So acceptor, or sometimes called as the recognizer, this is an automaton that computes a Boolean function, and it is called as the acceptor. So all the states of an acceptor is either accepting or rejecting the inputs. Classifier, it has more than two final states and it gives a single output when it terminates. Transducer, this is an automaton that produces output based on current input and previous state that is called the transducer. So there are two types of transducer. We have the milli machine and the Moore machine. When we say milli machine, so the output depends both on the current state and the current input. The Moore machine, the output depends only in the current state. So acceptability by DFA and NDFA. So a string is accepted by the DFA or NDFA if DFA and NDFA state starting at the initial state ends in an accepting state. Okay? So a string S is accepted by the DFA or NDFA using the 5-tuple notation. Okay? If the transition starts with the initial state and with an element of a final state. The language L accepts the DFA and DFA if S such that as S is an element of the language or the set of all possible strings, and the transition function has an initial state and with an element of a final state. Okay? So string S is not accepted by a DFA or NDFA if the transition function has an initial state, okay, but without an element of a final state. Okay? So if there is no final state, hence the string is not accepted by the DFA or NDFA. So the language not accepted by the DFA or NDFA is the complement of accepted language L. So meaning to say, the string is accepted such that the string is an element of the set of all possible strings, and the transition function contains the initial state, okay, and the string has, okay, contains without an element of the final state. Okay. So NDFA to DFA conversion, so this is possible by means of you also using the 5-tuple notation, okay, and then you are to convert it versus in the procedure given by the NDFA. So we have an algorithm here. So we have an input, an NDFA. We have the output equivalent of DFA. We have the steps. You have to create the table from the NDFA. So I think we're going to discuss again the transition function also contains the transition table. So we are to discuss this by next meeting. Step 2, create a blank state table under possible input alphabets for the equivalent DFA. Step 3, mark the starting state of the DFA by Q sub 0. So same with the NDFA. Step 4, find out the combination of the states. Okay, what are the states given for each possible input alphabet? Each time we generate a new DFA state under the input alphabet columns, we have to apply step 4 again. So otherwise, go to the step 6 wherein the state which contains any of the final states of the NDFA are the final states of the equivalent DFA. So again, we are to discuss the transition table by next meeting class. So next is DFA minimization using the Myfield-Nero theorem. So we have the algorithm here. We have the inputs, okay, input DFA, output minimize DFA. We have the steps. You have to draw the table for all pairs of the state, okay. Step 2, consider every state of the state pair. Step 3, repeat this step until we cannot mark any more states. Step 4, combine all the unmarked pair, okay, and make them a single state in the reduced DFA. So DFA minimization using equivalence theorem, if X and Y are two states in a DFA, we can combine these two states in X and Y, okay, if they are not distinguishable. So two states are distinguishable if there is at least one string, okay? So hence a DFA is minimal and only if all the states are distinguishable. So this is the algorithm tree for minimization. All the states Q are divided into two partitions. We have the final state and the non-final state, okay? So the non-final state is denoted by P sub 0. Step 2, increment K by 1 for each partition. So in PK, so PK will, you can use the variable PK, okay, for the partitioning. Okay, next, step 3, if PK is not equal to PK minus 1, you have to repeat step 2. Otherwise, go to step 4, then combine the kth element sets and make them the new states of the reduced DFA. So again, we are to go apply the applications for creating this state diagram, state table next meeting. So next is Moore and Mealy machine. So again, this was mentioned a while ago. So Moore and Mealy machine are the two types of finite state machine. Okay. So a Mealy machine is an FSM or finite state machine whose output depends on the present state as well as the present input. Now, the milli machine is presented by a 6-tuple notation. So this is the 6-tuple notation, wherein Q means states, the sigma or the summation symbol means alphabet, okay? And then this symbol, the O, is the finite set of symbols called the output alphabet. This means the transition function, okay? Then the X is the output of transition function. And the Q sub 0 is the initial state. So this is the 6-tuple notation. So this is what? This is the milli machine. Next is the Moore machine. So it is an FSM or the finite state machine whose outputs depend only on the present state. So a Moore machine is described also by a 6-tuple notation wherein you are to include the states, okay, the input alphabet, the output alphabet, transition function, the output of transition function, and the initial state. Okay? So this is for the Moore machine. So to compare the milli versus the Moore machine, so again, just to summarize, milli output depends both upon present and state and present input. Moore machine depends only on the present state. On milli machine, it has fewer states. Moore machine, more states. Milli machine, output changes at the clock edge. In Moore machine, input change can change in output change as soon as logic is done. In milli machine, it reacts faster to inputs. In Moore machine, more logic is needed to decode the output. Okay? So that is the summary of comparison for the milli and Moore machine. Okay? So this is the algorithm. So again, input is Moore, output is milli. Step 1, take a blank milli machine. Okay? Step 2, copy all the Moore machine transition states. Step 3, check the present states and their corresponding outputs in the Moore machine. Okay? Algorithm 5, okay? Input, milli machine, output, Moore machine. Step 1, you are to calculate the number of different outputs for each state. Step 2, if all the outputs of states are same, copy the state, okay? If there are distinct outputs, then you are to break in. Step 3, if the output of the initial state is 1, insert a new initial state at the beginning. So that's the end of our topic for today.